Hello, and welcome to Boring History for Sleep. Tonight we turn our attention to the silent, unassuming architects of modern efficiency. Consider for a moment the simple, ubiquitous beep of a scanner. It is a sound so common in our daily lives that it has become auditory background noise, the punctuation mark of a transaction, the confirmation of a process. Yet behind that instantaneous chirp lies a decades-long story of fierce competition, painstaking collaboration, and the meticulous construction of a universal language. It is a language not of words, but of lines and spaces, a syntax of light and shadow that quietly reorganized the physical world. This is the story of how the industrial barcode became the bedrock of modern logistics. But to truly understand this quiet revolution, we need to travel back to a time before the beep, to a world of clipboards and manual counts, and examine its origins. Our story begins not in a gleaming technological laboratory, but in the noisy, chaotic, and decidedly analog environment of the mid-20th century American factory and warehouse. Before the 1970s, the management of physical inventory was a profoundly human, and therefore profoundly fallible, endeavor. The fundamental unit of data collection was a person armed with a clipboard, a pencil, and a tally sheet. Imagine a vast warehouse, its shelves stretching high into the gloom, filled with thousands of different parts, each in its own bin or on its own pallet. The process of taking inventory was a monumental task. A team of workers would methodically walk the aisles, their eyes scanning handwritten labels or stenciled part numbers on wooden crates. They would count the items, make a tick mark on their sheet, and move to the next bin. This information, once collected, began a slow and perilous journey. The tally sheets were carried to a central office, where they were handed to a key punch operator. This was another critical and error-prone human interface. The operator would sit at a large clattering machine and translate the handwritten numbers from the sheets into a series of holes punched into stiff paper cards. Each card represented a single data entry, a single line item of inventory. A single misplaced punch, a misread number, or a smudged pencil mark on the original sheet could corrupt the data at its source. An entire day's worth of inventory counting for a large facility could result in thousands of these punch cards, which were then stacked into trays and physically carried to the company's mainframe computer, a room-sized machine that represented the pinnacle of data processing at the time. The cards were fed into a card reader, and only then, hours or even days after the physical count took place, could the computer generate a report on the state of the inventory. The potential for error was staggering. A study from the era suggested that a manual data entry process involving a human reading information and keying it in had an error rate of approximately one substitution for every 300 characters entered. In the context of a parts warehouse, with thousands of distinct items, each with a long alphanumeric part number, this was not a trivial matter. An incorrect part number could lead to a production line shutting down for want of a component that the system believed was in stock. An incorrect quantity could lead to phantom inventory, promising a customer an item that did not exist, or an unnecessary and costly reorder of an item that was already overstocked. The process was not only inaccurate, it was slow. The data was always lagging behind the reality on the warehouse floor. By the time an inventory report was generated, the physical state of the warehouse had already changed. It was a system perpetually looking in the rearview mirror. This was the fundamental problem that a new generation of engineers and logisticians sought to solve. They needed a way to bridge the gap between the physical object and its corresponding record in a digital computer. They needed a machine-readable language that could be affixed to any item, a language that could be read quickly, accurately, and without the need for human transcription. The concept was not entirely new. As early as 1948, a graduate student at Drexel Institute of Technology in Philadelphia, named Bernard Silver, overheard a conversation. The president of a local food chain was pleading with the dean to develop a system that could automatically capture product information at the checkout counter. The idea intrigued Silver, and he mentioned it to his friend, a fellow graduate student and former teacher named Norman Joseph Woodland. Woodland, a brilliant inventor, was captivated by the problem. He began to work on a solution. His first idea involved using patterns of fluorescent ink that would glow under ultraviolet light, but the ink was unstable and the printing was inconsistent. He then retreated to his grandfather's apartment in Miami Beach to focus on the problem. The breakthrough, as he would later recount, came to him on the beach. He was thinking about Morse code, the system of dots and dashes used in telegraphy. He began drawing dots and dashes in the sand. As he absent-mindedly extended the dashes downwards into long lines, an idea formed. He realized that if he could create a pattern of thick and thin lines, a machine could be built to read it. To make it omnidirectional, meaning it could be read from any angle, he wrapped the linear code around into a circle, creating a pattern of concentric rings that looked like a bullseye. On October 20th, 1949, Woodland and Silver filed a patent for their invention, which they called a classifying apparatus and method. U.S. Patent 2006-12994 was granted in 1952. The technology of the time, however, was not ready for their vision. Their prototype scanner was the size of a desk. It used a massive 500-watt incandescent bulb to illuminate the code, and a photomultiplier tube, a sensitive but fragile vacuum tube device borrowed from movie sound systems to read the reflected light. It was bulky, expensive, and impractical for widespread use. Woodland eventually went to work for IBM, and while the company briefly considered purchasing the patent, they ultimately concluded that the processing equipment required to make the system work was not yet commercially viable. The patent was eventually sold to Philco, and then to RCA, where it languished. The first major, albeit ultimately unsuccessful, attempt at a real-world implementation of automated identification came not from retail, but from another massive American industry with a logistics problem: the railroads. In the 1960s, the Association of American Railroads was struggling to keep track of its fleet of nearly 2 million freight cars, which were scattered across the North American continent. A system was needed to identify cars as they passed key checkpoints. The result was a system called CarTrack. It used a barcode-like symbology consisting of 13 horizontal stripes of retroreflective material in different colors: blue, orange, black, and white, applied to the side of each railcar. As the train passed a trackside scanner, a powerful xenon lamp would flash, and a series of photomultiplier tubes with colored filters would read the reflected pattern, identifying the car's owner and number. By 1967, the Association of American Railroads made the CarTrack system mandatory. A massive effort was undertaken to label the entire fleet of freight cars in North America. By the early 1970s, the vast majority of cars were labeled. However, the system was a failure. The labels, exposed to the harsh railroad environment, quickly became covered in dirt, grease, and snow, rendering them unreadable. The scanners were expensive to install and maintain. The system's accuracy rate never reached the required levels, and by the late 1970s, the industry abandoned the project. The CarTrack experiment, though a failure, was a valuable lesson. It demonstrated the immense challenge of creating a robust automatic identification system for a harsh industrial environment, and highlighted the absolute necessity of reliability and durability. While the railroads struggled, the grocery industry was revisiting the problem that had first inspired Woodland and Silver. The profit margins in the grocery business were razor-thin, and labor costs, particularly at the checkout counter, were a major expense. Supermarkets were getting larger, stocking more items than ever before, and the checkout process was a significant bottleneck. Each item had to be picked up by a cashier, who would look for a price sticker, key the price into the cash register, and then place the item on a conveyor. The process was slow and prone to errors. A system that could automate this process promised huge efficiency gains. In 1969, the National Association of Food Chains launched a formal effort to find a solution. They formed the U.S. Supermarket Ad Hoc Committee on a Uniform Grocery Product Code. This committee, a consortium of the industry's biggest players, established a set of guidelines for a scannable code. The symbol had to be small, printable on existing packaging, and readable with a high degree of accuracy by a non-contact scanner. Crucially, it needed to be standardized. Every manufacturer would have to use the same code, and every supermarket would have to use scanners that could read it. This was a monumental undertaking in industry-wide cooperation. Several major technology companies submitted proposals. RCA, which now owned the Woodland and Silver patent, proposed their Bullseye code. It had the advantage of being omnidirectional. IBM, where Norman Joseph Woodland now worked, also entered the fray. A team led by engineer George Laurer was tasked with developing a symbol. Laura's team reviewed the Bullseye, but found it had a significant drawback. During the printing process, the ink could sometimes smear, and a circular smear would render the entire code unreadable. A linear code, by contrast, could tolerate some vertical smearing without losing its data. Laura's team developed a rectangular, linear symbol that packed the required data into a small space. It was a fixed-length numeric-only code, specifically designed for the needs of the grocery industry. In April 1973, after extensive testing and heated debate, the committee made its decision. They selected the IBM proposal. The symbol became known as the Universal Product Code, or UPC. The first digit of the code identified the product category, the next 5 identified the manufacturer, and the following 5 identified the specific product. A final check digit was added to ensure reading accuracy. The Uniform Code Council was established to administer the new standard, assigning manufacturer numbers and maintaining the integrity of the system. The stage was set. All that was needed was the technology to read the code efficiently. The development of the laser was the key enabling technology. Helium neon lasers, which produced a coherent red light, were now reliable enough for commercial use. Companies like Spectra Physics and Symbol Technologies developed scanners that used a laser beam, deflected by a rotating mirror, to sweep across the UPC symbol hundreds of times per second, ensuring a read regardless of the item's orientation. On June 26, 1974, at a Marsh supermarket in Troy, Ohio, the first official UPC scan took place. A cashier named Sharon Buchanan scanned a 10-pack of Wrigley's Juicy Fruit chewing gum. The cash register beeped and registered the sale. The quiet revolution had officially begun. The adoption of the UPC was a watershed moment. It proved that a large-scale, standardized automatic identification system was not only possible, but also immensely valuable. However, the UPC was a highly specialized tool for a very specific job. Its numeric-only, fixed-length format was perfect for identifying consumer products at the point of sale, but it was wholly inadequate for the complex world of industrial manufacturing and logistics. The industrial environment had a different set of requirements. In a factory or a warehouse, you needed to track more than just a product a customer was buying. You needed to track individual components, batches of raw materials, subassemblies, tools, and shipping containers. These applications required a code that could handle not just numbers, but also letters, an alphanumeric code. They also needed the ability to encode a variable amount of information. A part number might be 7 characters long, while a serial number might be 15. A fixed-length code like the UPC would be incredibly wasteful. Furthermore, the printing technology available in most factories was not the high-precision lithography used for retail packaging. It was often dot matrix or impact printers, which were less precise. The symbology needed to be robust enough to be printed by these methods and still be readable. This need for a more flexible, industrial-strength barcode led to the development of a number of competing symbologies in the early 1970s. One of the earliest was called Code 2 of 5. Developed by Identicon Corporation, it was a numeric-only code, but it introduced a simple and effective encoding scheme. Each digit was represented by 5 bars, 2 of which were wide and 3 of which were narrow. Another variation, Interleave 2 of 5, was developed by Dr. David Allais at Intermec. This version was more compact because it encoded information in both the bars and the spaces between them. A digit would be encoded in the 5 bars, and the next digit would be encoded in the 5 spaces that followed. This made it much denser, but it was still numeric only. Plessy code, developed in the UK, was another early contender, used primarily in libraries and for shelf marking. The real breakthrough for industrial applications came in 1974, the same year the first UPC was scanned. It came from Dr. David Allais and Ray Stevens at Intermec Corporation, a company based in Everett, Washington, that was a pioneer in barcode technology. They developed a new symbology they called Code 39. The name was derived from its structure. Each character in the code was composed of 9 elements, 5 bars and 4 spaces. And 3 of these 9 elements were always wide, while the other 6 were narrow. This structure gave the code a powerful property. It was self-checking. If a single element was misread due to a printing flaw or a smudge, it would result in a character that did not conform to the 3 of 9 rule. The scanner's decoder would immediately recognize this as an invalid read and would not transmit any data. This inherent robustness made it far less likely to substitute one character for another, a critical requirement for industrial applications where a single wrong digit in a part number could have serious consequences. But the most important feature of Code 39 was its character set. It was the first widely used symbology that could encode the full uppercase alphabet from A to Z, the digits 0 through 9, and a handful of special symbols including the hyphen, period, and space. It was a true alphanumeric code. It was also a discrete, variable length symbology. Each character was encoded independently and was separated from the next by a narrow intercharacter gap. This meant that a barcode could be as long or as short as the data required. To mark the beginning and end of the code, Code 39 used a special start-stop character, which was represented by the asterisk symbol. A scanner would not begin decoding until it saw the unique bit pattern of the asterisk, and it would continue reading until it saw the closing asterisk. This allowed the scanner to read the code bidirectionally, from left to right or right to left. Code 39 was not the most data-dense symbology. Its wide, narrow structure and the intercharacter gaps meant that it took up a fair amount of physical space to encode information. But in the 1970s and early 1980s, this was less of a concern than reliability and simplicity. And Code 39 was simple. It was relatively easy to generate the printing instructions for it, and it could be printed reliably with the dot matrix and early thermal printers that were common in industrial settings. It was a rugged, versatile, and straightforward solution, a perfect fit for the factory floor. Despite its technical advantages, the widespread adoption of Code 39, or any industrial barcode, was not a foregone conclusion. For a barcode system to be effective in a supply chain, it requires standardization. A parts supplier needs to be able to put a label on a box that can be read by the assembly plant that receives it. Without a common standard, companies would exist in a Tower of Babel of different symbologies, defeating the purpose of automation. In the late 1970s and early 1980s, 2 powerful forces emerged that would drive the standardization process and cement Code 39's dominance in the industrial world: the U.S. Department of Defense and the American automotive industry. The U.S. military has always been one of the world's largest and most complex logistical organizations. By the late 1970s, the Department of Defense was managing an inventory of more than 4 million distinct items, spread across hundreds of depots, bases, and ships around the globe. The system for tracking this mountain of material was still largely paper-based. The error rates were high, visibility was low, and the cost of managing the supply chain was enormous. The military recognized that it had a data entry problem of epic proportions and saw the potential of barcode technology to solve it. In 1981, the Department of Defense initiated a program called LOGMARS, which stood for Logistics Applications of Automated Marking and Reading Symbols. The goal of the program was to select a standard barcode symbology and implement it across the entire defense supply chain. This was an undertaking of incredible scale. A team was formed to study the available technologies and symbologies. They evaluated Code 39, Interleave 2 of 5, and several others. Their final report overwhelmingly recommended the adoption of Code 39. They cited its alphanumeric capability, its high degree of self-checking and accuracy, and its ease of printing as the primary reasons for their choice. In 1982, the Department of Defense published Military Standard 1189, which formally established Code 39 as the standard symbology for marking all property procured by the U.S. military. This was followed by Military Standard 129, which specified the exact format and placement of barcode labels on shipping containers. The impact of the Logmar's decision cannot be overstated. It sent a clear and powerful signal to the market. Suddenly, tens of thousands of defense contractors, from huge aerospace companies to small machine shops, were required to put Code 39 barcodes on their products and shipping containers if they wanted to do business with the government. This mandate created a massive, guaranteed market for barcode equipment overnight. Companies that manufactured printers, scanners, and labels saw a surge in demand. This volume drove down the price of the technology. A laser scanner that might have cost several $1,000s in the late 1970s saw its price fall dramatically. The Logmar's program effectively funded the maturation of the industrial barcode industry. It spurred innovation in scanner design, label adhesives, and printing technology, all of which benefited the commercial sector as well. At the same time that the military was mandating barcodes, a similar movement was underway in another pillar of the American economy, the automotive industry. In the early 1980s, American carmakers were facing intense competition from Japanese manufacturers. A key element of the Japanese success was their mastery of just-in-time, or JIT, manufacturing. JIT is a production strategy that aims to minimize inventory and increase efficiency by supplying parts to the assembly line only as they are needed. For JIT to work, a company needs to have extremely accurate and real-time information about its supply chain. You need to know exactly what parts you have, where they are, and when they will arrive. The old paper-based systems of the American auto industry were simply not up to the task. In 1981, executives from General Motors, Ford, and Chrysler, along with their major suppliers, formed a cooperative organization to address this challenge. They called it the Automotive Industry Action Group, or AAG. The AAIG's mission was to work on common business process and technology standards that would improve the efficiency of the entire industry. One of their first and most important tasks was to develop a standard for shipping and parts identification. Like the Department of Defense, they embarked on a study of barcode symbologies, and, like the Department of Defense, they concluded that Code 39 was the best choice for their needs due to its alphanumeric character set and its reliability. In 1984, the AIAG published its first barcode standard, known as AAG B1. This standard specified the use of Code 39 and defined a standard format for a shipping label that would be applied to all containers of parts sent from a supplier to an automotive plant. The label was meticulously designed, with specific locations, or zones, for different pieces of information. It included the part number, the quantity of parts in the container, the supplier's identification number, a serial number for the container, and other critical data, with each piece of information presented in both human-readable text and a Code 39 barcode. The adoption of the AIAC standard had an effect similar to the Logmar's program. It forced thousands of companies in the automotive supply chain to adopt barcode technology. A supplier that made something as simple as lug nuts had to invest in printers and software to generate the AIAG-compliant labels for their shipments to Ford or GM. The receiving docks at the assembly plants were equipped with barcode scanners. When a truck arrived, a worker could simply scan the label on each pallet. The system would instantly know that a specific quantity of a specific part from a specific supplier had arrived. This data could be used to update inventory records, direct the pallet to the correct location in the warehouse or directly to the assembly line, and even automatically trigger a payment to the supplier. The manual process of checking packing slips and keying in data was eliminated. The speed and accuracy of the receiving process improved dramatically, which was a critical enabler for just-in-time manufacturing. The convergence of the military and automotive industries on Code 39 as their standard created a powerful network effect. With two of the largest manufacturing sectors in the country using the same symbology, Code 39 became the de facto standard for industrial barcoding in North America for the remainder of the 1980s. This standardization was the key that unlocked the full potential of the technology. While the standards for the symbologies themselves were solidifying, the technology used to read them was undergoing its own rapid evolution. The first generation of scanners were relatively simple devices. The most common was the wand scanner, also known as a light pen. This was a handheld device shaped like a thick pen, with a light source, usually a red light-emitting diode, or LED, and a photodetector in its tip. To read a barcode, the user had to place the tip of the wand in contact with the label and drag it across the entire code at a steady speed. The photodetector would measure the light reflected back from the black bars and white spaces. The decoder circuitry, either in the wand itself or in a connected terminal, would translate this analog waveform of light and dark into digital data. Wand scanners were inexpensive and durable, but they required a certain amount of skill to use effectively. If the user moved the wand too fast, too slow, or at an angle, it would result in a misread. They also required direct contact with the label, which could cause wear and tear over time. The major leap forward in scanning technology was the helium neon laser scanner. Unlike a wand scanner, a laser scanner is a non-contact device. It can read a barcode from a distance of several inches to several feet. Inside the scanner, a low-power helium neon laser tube generates a thin, intense beam of red light. This beam is directed at a small, oscillating mirror or a rotating, multifaceted prism. This moving optical element sweeps the laser beam back and forth across the barcode symbol hundreds of times per second. A photodetector inside the scanner captures the light that is reflected back from the label. When the beam crosses a white space, a large amount of light is reflected back. When it crosses a black bar, most of the light is absorbed. This creates a rapidly fluctuating signal that corresponds to the pattern of the barcode. Sophisticated decoding algorithms analyze this signal, filter out noise, and reconstruct the data encoded in the symbol. Laser scanners were a game changer for industrial logistics. A worker on a receiving dock could now scan a pallet on a forklift from a comfortable distance. Fixed-mount laser scanners could be installed over conveyor belts, automatically identifying and routing thousands of cartons per hour without any human intervention. They were faster, more aggressive in reading poorly printed or damaged codes, and far more ergonomic to use than wands. While initially expensive, the demand created by the LogMARS and AIAG initiatives drove their prices down, making them accessible to a wider range of businesses. By the late 1980s and early 1990s, another type of scanning technology began to emerge, challenging the dominance of the laser. This was the charge-coupled device, or CCD scanner. A CCD is a solid-state electronic component, an array of tiny light-sensitive elements. Instead of sweeping a single point of light across the code, a CCD scanner uses a row of LEDs to illuminate the entire barcode at once. A lens then focuses an image of the barcode onto the CCD chip. Each element in the CCD array measures the intensity of the light hitting it, effectively taking a one-dimensional picture of the barcode. The processor then analyzes this picture to decode the pattern of bars and spaces. CCD scanners had several advantages over lasers. They had no moving parts, like the oscillating mirror in a laser scanner, which made them more rugged and durable, a significant benefit in a rough industrial environment. They were also more energy efficient. Their main limitation, at least initially, was their short read range. They had to be held within a few inches of the barcode to capture a clear image. However, as the technology improved, their performance increased, and they became a popular and cost-effective alternative to laser scanners, particularly for handheld applications. The final piece of the hardware puzzle was the device that the scanner was connected to. In the early days, a scanner was often tethered to a stationary computer terminal. This was fine for a fixed checkout counter or a conveyor belt, but it was not practical for a worker who needed to be mobile in a large warehouse. This led to the development of portable data terminals. These were rugged, handheld computers with a built-in barcode scanner, a small display, and a keypad. They had their own memory and processing power. A worker could walk through the warehouse, scanning items for an inventory count or a picking order, and the data would be stored in the terminal's memory. At the end of their shift, or when the task was complete, they could return the terminal to a cradle, which would download the collected data to the main computer system. This untethered the worker from a fixed station and brought the power of data collection directly to the point of activity. The communication between the scanner or terminal and the host computer also evolved. Early systems often used a standard serial connection, like an RS-232 port. A more ingenious solution was the keyboard wedge. A keyboard wedge was a small device or a piece of software that connected the scanner between the keyboard and the computer. When a barcode was scanned, the data was sent to the computer as if it had been typed on the keyboard, followed by an enter keystroke. This meant that a barcode scanner could be added to almost any existing computer system without any special software. The data from the scan would simply appear at the cursor, wherever it happened to be on the screen, be it a spreadsheet, a database form, or a word processor. This simple but brilliant interface greatly accelerated the adoption of barcode technology, as it made integration with legacy software systems incredibly easy. By the early 1990s, the ecosystem of industrial barcoding was mature. Code 39 was the dominant symbology, and a variety of robust and affordable scanning technologies were available. The benefits were clear. Data accuracy improved dramatically, labor costs for data entry were slashed, and companies gained an unprecedented level of real-time visibility into their operations. However, as supply chains became more complex and the demand for information grew, some of the limitations of Code 39 began to surface. The primary limitation was its data density. Because of its 3 of 9 structure and discrete nature, Code 39 takes up a relatively large amount of space to encode data. As companies wanted to put more and more information onto a single label, part numbers, serial numbers, lot numbers, expiration dates, the barcodes were becoming excessively long. A very long barcode can be difficult to scan, and on small items there simply wasn't enough room to print it. A new symbology was needed, one that could pack more information into a smaller space without sacrificing reliability. The answer came in the form of Code 128. Developed in 1981 by Computer Identics Corporation, Code 128 was a much more sophisticated and data-dense symbology than Code 39. As its name suggests, it can encode all 128 ASCII characters, including uppercase and lowercase letters, numbers, punctuation, and even non-printable control characters. Unlike Code 39, which uses a simple wide, narrow scheme, each character in Code 128 is represented by a pattern of 3 bars and 3 spaces, with a total width of 11 modules. The specific pattern of these bars and spaces determines the character. The true genius of Code 128 lies in its 3 different character sets, which can be switched between within a single barcode to optimize for data density. Character set A includes the standard uppercase letters, numbers, punctuation, and control characters. Character set B includes uppercase and lowercase letters, numbers, and punctuation. Character set C is a numeric-only set, but it is extremely efficient. It pairs up digits and encodes each 2-digit pair from 00 to 99 as a single character. This means that a long string of numbers can be encoded in roughly half the space it would take using character set A or B. A Code 128 barcode can start in one character set, use a special shift character to move to another set to encode a different type of data more efficiently, and then shift back. This flexibility made it far superior to Code 39 for applications that required a mix of alphabetic and long numeric data strings. Code 128 also included a more robust check-digit system. While Code 39 was self-checking on a per-character basis, it did not typically require a full symbol check digit. Code 128, on the other hand, mandates a modulo 103 check digit. This is a weighted checksum calculated across all the data characters in the symbol. The scanner's decoder performs the same calculation on the data it reads and compares the result to the check digit encoded in the symbol. If they don't match, the scan is rejected. This makes the probability of a substitution error in a Code 128 barcode infinitesimally small. For several years, Code 128 was a powerful but niche symbology. Its adoption was accelerated when the Uniform Code Council, the same body that administered the UPC for retail, saw its potential for logistics and supply chain applications beyond the grocery store. They created a new standard based on Code 128, which they called UCC EAN 128, later renamed GS1 128. This standard was more than just a symbology. It was a data structure. It introduced a system of application identifiers, or AIs. An AI is a 2 to 4 digit prefix that tells the computer system what kind of data follows. For example, the AI01 indicates that the following data is a global trade item number. The AI10 indicates a batch or lot number. 17 indicates an expiration date. 30 indicates a count of items. A single GS1128 barcode could now contain multiple pieces of information, each clearly identified by its AI. A label on a pallet of perishable goods could have one long barcode that encoded the product ID, the lot number, and the expiration date. When this barcode was scanned at the receiving dock, the warehouse management system would not just get a string of characters, it would get structured data. It would know to pass the data following AI01 as the item number, the data following AI10 as the lot number, and so on. This allowed for much more sophisticated automation. The system could automatically check the expiration date and flag the pallet for first in, first out handling. It could track inventory not just by product, but by specific lot, which is critical for food, pharmaceutical, and other regulated industries. The adoption of the GS1128 standard in the 1990s marked a significant shift in the use of barcodes in logistics. It moved beyond simple identification to the transmission of rich, structured data about the product and its journey through the supply chain. While Code 39 remained a workhorse for many internal and less complex applications due to its simplicity, GS1128 became the standard for shipping, logistics, and compliance labeling in a vast number of industries. By the mid-1990s, the barcode was a mature and ubiquitous technology in American manufacturing and logistics. The processes it enabled had become standard operating procedure. A typical distribution center of this era was a finely tuned machine, orchestrated by the flow of data from barcode scans. When a truck from a supplier arrived, its contents were unloaded onto a receiving dock. A worker with a handheld radio frequency terminal would scan the GS1128 label on each pallet. This single scan would tell the warehouse management system, or WMS, everything it needed to know about the product. The WMS would verify that the shipment matched the purchase order and then direct the worker on where to store the pallet. It might instruct the forklift driver via their terminal to take the pallet to aisle 14, Bay 6, level C. When the pallet was put away, the worker would scan the barcode label on the shelf location to confirm that the pallet was in the correct place. The company now had a perfect real-time record of that product's existence and location in its inventory. When a customer order was received, the WMS would generate a picking list. A worker, again with a handheld terminal, would be directed through the warehouse in the most efficient path to pick the required items. At each location, they would scan the shelf and then the product to confirm that they were picking the correct item. This process, known as scan verification, dramatically reduced picking errors. Once all the items for an order were gathered, they were taken to a packing station. Here, they were packed into a shipping carton, and a final shipping label was generated. This label would typically include a barcode with a tracking number from a carrier like UPS or FedEx. As the carton moved through the carrier's network, this barcode would be scanned at every step, providing end-to-end visibility of the shipment for both the sender and the receiver. This entire ecosystem, from the supplier's factory to the distribution center to the final customer, was held together by the humble barcode. It was the data capture mechanism that fed the computer systems that managed the physical flow of goods. It was the language that allowed the systems of different companies in a supply chain to communicate with each other in a standardized way. As the 1990s drew to a close, the limits of even one-dimensional barcodes like Code 128 were being reached. The amount of information that companies wanted to link to a physical item continued to grow. For example, the electronics industry needed to track not just a part number, but also the specific revision level, date of manufacture, and country of origin on very small components. A one-dimensional barcode to hold all this data would be impractically large. This need for even greater data capacity in a small space led to the development of two-dimensional or 2D symbologies. Unlike a 1D barcode that encodes data in a single row of bars, A 2D code encodes data across a two-dimensional pattern of squares, dots, or hexagons. One of the earliest and most influential 2D codes was PDF 417. Developed by Symbol Technologies in 1991, PDF 417 looks like a distorted, grainy rectangle. It is a stacked linear barcode, composed of multiple rows of a linear code stacked on top of each other. PDF stands for Portable Data File, and it was capable of encoding over a kilobyte of data, a massive increase over any 1D code. This meant it could encode not just an identifier, but an entire data file, a shipping manifest, a bill of lading, a technical specification, or a patient's medical record. PDF 417 found widespread use in logistics for printing shipping manifests directly on a package, and it was adopted by departments of motor vehicles across the country for encoding the driver's information on the back of a driver's license. Another 2D symbology that emerged in this period was the QR code, or quick response code, invented in Japan in 1994 by a subsidiary of Toyota. Its distinctive pattern of 3 large squares in the corners allowed it to be read at very high speeds. While it would not become a consumer-facing phenomenon until the age of the smartphone, its ability to store a large amount of data and its error correction capabilities made it attractive for manufacturing applications, particularly for tracking parts through the automotive assembly process. The advent of these 2D codes marked the next step in the evolution, moving from a simple license plate to a portable, self-contained database affixed directly to an object. The period from 1970 to 2000 was a time of transformative change in American manufacturing logistics, a change that was enabled and accelerated by the meticulous evolution of barcode technology. It was a journey from the chaos of manual counting and key-punch data entry to the ordered, real-time precision of the modern, system-directed warehouse. It was a story driven by needs: the need for speed at the checkout counter, the need for accuracy in the military supply chain, the need for efficiency on the automotive assembly line. It was a story of ingenious invention, from Woodland's flash of insight on a Miami beach to the sophisticated data structures of Code 128. And most importantly, it was a story of painstaking collaboration and standardization. The committees and action groups, the military standards, and industry-wide mandates, these were the unsung heroes of the barcode revolution. They did the slow, difficult, and often tedious work of getting everyone to agree to speak the same language of lines and spaces. The result of their work is the invisible infrastructure that underpins modern commerce. The simple beep of the scanner is the sound of that infrastructure at work. It is the sound of data being captured without error, of inventory being updated in an instant, of a package being routed to its correct destination. It is a sound that signifies a world made more orderly, more efficient, and more interconnected. And so, as you settle in to rest, perhaps you can appreciate the quiet, profound order in that simple, repetitive sound. A sound that represents a long and meticulous journey from a world of paper and guesswork to a world of light, logic, and the silent, elegant language of the barcode. A language that brought a new kind of clarity to the complex dance of making and moving things, one scan at a time.